Hello, everybody. Can everyone hear me? That was supposed to be a joke. Just to demonstrate that there is food at the seminars, I'm still finishing chewing my last mouthful. I'm sure that you all appreciate me sharing that. But moving on, it's my great pleasure to introduce Danny Abrams, is the new co-director at NICO. And it's someone that for a long, long time has been doing extraordinary work in complex systems. So he got his bachelor's degree at Caltech and then his PhD in theoretical and applied mechanics. And you may wonder why. And that's because that was the department where Steve Strogatz was. And I think that was the reason why you went there. And so he has been using the kind of simplified, idealized mathematical modeling that is able to really extract powerful insights about complex systems. And he has used them on a number of topics, from synchronization to left-handedness to, as we heard a few days ago, fashion and all of that stuff and collaborations. So I'm sure that we are in for a treat. And I have to leave before the end for another appointment, so I will be not pestering him with questions. And I don't think Danny will feel at home if no one pesters him with questions. So I know it's a tough ask, but please do. So let's all welcome Danny.
Thank you, Luis, for the very nice intro there. I'm going to talk about, as the title says, tractable mathematical modeling, particularly in this context of social systems. I would say, as Luis mentioned, my work is more complex systems. I see that as a superset, and social systems is somewhat of a subset. And I say some successes and failures, maybe failures needlessly harsh, things that haven't succeeded yet. But I think it's useful to talk about those in addition to just successes. Because that's often how it goes. You'll see I actually have a list that's much longer of things that have not succeeded. Before I get started with that, also, as Luis mentioned, I am the new co-director of NICO from McCormick School, Brian Utzi being the co-director from Kellogg. As part of that, I want feedback. So please, I'll put a reminder at the end also. Send me your thoughts if you have thoughts on things that you wish NICO were doing more of, things that you think it's doing well, things that you think it's not doing well. I'm looking for feedback, so keep that in mind as a preface. Also, a warning, this talk is actually going to be almost more like philosophy of modeling. I kind of expanded the scope a little bit, maybe a little bit too much, but hopefully it'll be of some interest. And before I go to my first slide, beyond the title slide here, I want to ask, does anyone recognize, I'm just curious, does anyone recognize the artwork that's in the background here? Or have any idea who the artist is? Oh, that's great. That's a good thing. All right, we'll get to it. It's going to be in the talk also. But I'll leave it a mystery for now. So, that said, change. Okay. What is a model? So that's going to be my starting frame of this talk. I want to talk about why tractable mathematical modeling is useful. But first, I want to talk about what a model is, because I'd say I'm going to list here like 6 different interpretations or definitions of what a model is. And there's more out there too. These are just 6 common ones. So the first broad way that the word model is interpreted, I think, is as a conceptual model. This is maybe the most common in social sciences, but it's throughout science. So I'm going to give some examples throughout this from my own research. One example of a conceptual model is this thing called the fighting hypothesis. So this is a hypothesis for why people, here's an image, why people are left-handed today, and why isn't everybody right-handed? Why didn't we all converge on one laterality? It's a disadvantage in most of life to be left-handed. You are more susceptible to injury in a wide variety of ways, and in particular when using tools, if you're left-handed, because tools are typically designed for right-handers. But it's more than just tools. Power tools are terrible for left-handers, but in general, the world is built for right-handers, since left-handers are this small minority of only about 10% of the population. But the fighting hypothesis says that in the context of physical fights or physical confrontations, being left-handed, being different is an advantage. And this is an advantage of, this is an example of that in boxing. Manny Pacquiao, a few years ago, was considered the best boxer in the world, is a southpaw or left-hander. So he's been in this setup where he's facing a right-hander many times. Like if you were playing randomly, 9 times out of 10, if his opponents were random, 9 times out of 10, they would be right-handers. So he'd be in this situation 90% of the time. His opponent would only have been in this situation 1 out of 10 times. So there's this strong selection for people who are different in the context of physical fights or confrontations. So that was the conceptual model that existed before I worked on that project. I'll come back to this a little bit later in the talk. It doesn't say anything about math or computing or anything else. Here's one more example, the handicap principle, also from a different project I worked on. This says that, sometimes known as the Zahavi handicap principle. It says that the Darwin touched on this a little bit in some of his writing. So you might ask, why do deer have these elaborate antlers? Why do peacocks have elaborate, colorful feathers? This hypothesis or this principle states that those things exist because they're detrimental to survival of the animal. In fact, if they weren't detrimental to their survival, they would be useless. The whole purpose is to signal fitness, and in order for it to be honest, it's got to be costly. So that's the conceptual model there, that they're costly. There's a cost to having ornaments. So in this case, the cost is that it can literally get deer stuck in trees. It happens not a non-negligible amount of time. So here's another way that often conceptual models are shown, like diagrams, words or diagrams, right? Kind of big ideas. X here, like, it's just a generic diagram, but X causes M or Y, but W maybe influences how X influences those other 2 variables. So that's big concepts, not equations. And I think that is, in some sense, the goal of science, to get these big concepts down and figure out what's right. Okay, another interpretation of the word model in the context of more of statistics and econometrics, it's this idea that you can kind of use regression to fit a line to data, or not necessarily a line, any kind of curve. But often you start with linear regression, or you might have multivariable regression where you take the same data, but you assume there's other correlates besides just one X variable. I have a question for you all in the audience. So here's some data. This is real world data. I have hidden the axis labels. And I want you to just think about, you can feel free to raise your hand and give me your thoughts, but maybe some of you recognize it. But think about what you think the relationship between X and Y is on this graph. Give you like 10 seconds to sketch it or imagine sketching it. Not at all obvious to me. There's a lot of this like high frequency up and down stuff. Some of the data is kind of overlapping. Yes, hey, Gene. It is a time series, that's right. Very good. Pretty good at periodic. Yeah, it's very close to periodic, I'll say that. I'll reveal in just a second. I feel like there's also like this broad sort of low frequency thing, and then there's also some high frequency stuff. But I know the answer, so it's easy for me to say that. Okay, so what are the axes? Oh, I forgot to reveal that. What's the relationship here? So the axes here are date, so it's time series. Hey, Gene got it right. And declination of Mars, as observed by Tycho Brahe, massacring his name, I'm sure. The Danish astronomer in the late 1400s, 1500s. So his data were what ultimately led to Kepler's laws. Kepler interpreted this data to come up with his laws of planetary motion. He figured out that the orbits were ellipses, that the square of the period of orbit was equal to the cube, proportional to the cube of the semi-major axis of that ellipse. Like these very actually pretty simple conceptual ideas from this pretty messy data. Here's the actual orbit, and here's the same data overlaid on the modern calculation of what the orbit was. The data was actually amazingly good. But could you have discovered like these simple laws with statistical principles? I think it's a lot harder when you start from looking top down at the data. So yes, Hijin. Yes, it would look like an. That's a. Yes, that's a very good point. So yeah, there's a role for something else, which I'm going to get to, which is the simple mathematical models, which is what led Kepler to come to this conclusion, right? He was looking for something that was simple and beautiful, doesn't have a lot of parameters. So parsimony is a big, important part of what I'll call tractable mathematical modeling. But there's a role for both. Obviously, I'm not saying that the statistical approach isn't useful. Other meanings of the word model, especially today, more and more people are talking about machine learning as a model or machine learning models. I think there's nothing that comes close to how well machine learning can perform at like image classification tasks, like take a bunch of pixels and tell me if it's a cat or not. I don't think any other approach has ever come close. But this is kind of the strength of machine learning is classifying things. So either classifying points or maybe predicting the next point in the sequence. So here it's kind of trying to find a boundary between two different classes of points. Here it's trying to discover if there are clusters. And there are lots of different methods of machine learning. The big disadvantage is that's kind of a black box, at least some of the most popular methods. You don't necessarily know how it comes up with the result it comes up with. And so it's not easily interpretable. So there are methods that are more interpretable. Computational models I'll split into, this is number 4, I'll split that into 2 classes here. Agent-based models, which here's a big example, NetLogo, developed by Uri Walensky here. So in the agent-based models, you get the advantage that you can just specify kind of microscopic dynamics and then hit go and see what it leads to. So that's perfect for where we have kind of conceptual models at the microscopic level, and we want to see how it can lead to macroscopic behavior. But the big disadvantage is that you have to choose the parameters in any particular simulation. Here there's 5 different sliders. And so there's a lot of exploration of parameter space if you want to know everything that a model can do. And maybe it becomes, could even become prohibitively difficult to explore that parameter space when there are a lot of parameters. Differential equation-based computational models. This is just the common method called Runge-Kutta, but F would be some complicated differential equation in general or set of differential equations. Again, I think there's an important place for that when you have what you think are like ground truth principles. But when the function is very complicated, you don't get a lot of intuition or insight from it. And in addition, you have the same problem as with agent-based modeling, that you'll have a lot of parameters. And if you have a lot of parameters anyway, you won't necessarily know what the model can do without what could be a very costly exploration of parameter space. So now mathematical modeling, I would say this is my strength and the focus of this talk. And by mathematical, I'm implying sort of tractable mathematical models. So here's one example from my own research, a really simple ordinary differential equation. In fact, I am on time. I'll derive it a little bit later in the talk. Here, there's even 2 unknown functions for which let's say I know some limiting properties of that function. This is actually, just to give a little context, this is the fraction speaking language X. Fraction is lowercase x. And Y represents language Y. So this is a rate of transition from language Y to language X, rate from X to Y. It's a model for how people switch languages in a region where multiple languages are spoken. And the big advantage of a tractable model like this is you can make a picture. One big advantage, you can make a picture like this of a basin of attraction. So we don't have to try out a bunch of different initial conditions. We can analytically discover there's this boundary curve. And if you start anywhere over here with this initial fraction, speaking language X, and this status of the language between 0 and 1, you're going to end up with everyone speaking language Y. If you start on the other side, language X. So this is an example of why this analytical approach can be powerful. Even if you think other things are happening, it's a good starting point. Another thing you can get from these analytical approaches is, in this case, this comes from some work I've done on the evolution of left-handedness, again, as I mentioned with the fighting hypothesis. Here, one parameter in that model is cooperativity of society. What fraction of the time are we cooperating versus fighting or competing? And you can get bifurcations or tipping points out of these models. You can observe that that exists. In this case, society, according to this model anyway, if we had less cooperation, society would be about 50% right-handers, 50% left-handers. But then you pass some threshold, probably not precisely this on the scale of 0 to 1. The point is to get the big idea here. And you jump to a state where 90% of people are right-handed, or perhaps 90% could have been left-handed. During evolution, maybe there was some symmetry breaking. But of course, there's this philosophical thing that if 90% were left-handed, then we'd probably call left-right. So it's almost inevitably right-handed. Right, as an aside, the word right in most languages means like correct, like in English, or good. And where left usually means bad in some way. So it's what? Oh, yeah. Sounds sinister. Yes, exactly. So yeah, in English, I've looked up, in English, it comes from a Frisian word, this Dutch dialect that that meant bad in some way. It's almost every language, it traces back to something like that, or sometimes like clumsy. So, okay, anyway, enough getting off track. So mathematical modeling, that's my pitch for why I think mathematical modeling is very important, doing this, is taking this tractable approach. And then there are some more details here. You can take a mechanistic approach, which I would say is appropriate for problems where you have hypotheses at like the micro scale of what people are or what's happening, and build up the macro scale, what's happening at an individual level, from what happens at an individual level to the population, or an empirical model where you kind of hypothesize things about the way the population may be behaving, and then maybe compare that to data. It's also stochastic, whether in some cases randomness is key to understanding a phenomenon, but we can also, in many cases, kind of ignore it and just assume it blurs things. But that's a strong assumption. This is getting kind of into the weeds of the ways you can construct mathematical models. I think the big picture is that tractable models have a valuable place in this set of different ways we can think about modeling. And then the last one, I told you there were 6 actually. The last one is in a way a joke. The mouse model is like one of many examples of models in medicine, but yet it can lead to misunderstandings. People talk about models all the time, and you don't necessarily know that they're talking about like the animal versus like some computer simulation or something. So anyway, it's in the computer science sense, it's a heavily overloaded word, model. It can mean a lot of different things, but I think all these approaches are complementary, particularly first 5. So it's useful to be aware of the differences. So just to now emphasize a little bit more about the role for math. So insight, I think, is the goal of this tractable mathematical modeling, more than reproducing data precisely. So I told you that image was going to come back. So this is from an artist. I think the second image is the one I had at the start. So this is from 1907. So the artist is Pete Mondrian. I always thought it was P.A., but it's evidently pronounced Pete, like the American name. So Pete Mondrian was active in the early 1900s. So I think this was 1907 and then maybe 1908. He started with figurative art that depicted the world relatively realistically. And then he started moving to more abstract things. And probably everyone will recognize at least like the final image in this sequence I'm going to go through. So you can see, as this is almost like 1 year for each one of these paintings. He's getting more and more abstract here. And by the way, before I continue, I'll keep showing more. This is a very meta slide. This is my conceptual model of what the purpose of mathematical models is. If that makes any sense. The conceptual model being communicated by the sequence of images. So abstraction, I think, is a key insight, is a key to mathematical modeling. So he's getting more abstract. He added, so that last picture on the right, you can kind of see how maybe it connects to the tree. He's getting like branches are now like all horizontal and vertical. He's only got like a few curvy things, almost everything's a line. And he starts experimenting with colors, but he's still sticking with this like horizontal, vertical axis of most things in the image. Then he kind of flips this vertical thing with an kind of oval shape inside the canvas. adding more different colors. It's just, and then he takes away these lines, these strong lines he has everywhere. But then he changes his mind. He doesn't like that. He starts putting the lines back here and there. And then he goes to this like set of rectangles. Oh, the controls are blocking things here. So he goes to this set of rectangles, and then he goes to like equal size squares. And by the end, he's at this this bright solid color set of like interlocking rectangles, that primary color, I should say, not just solid color, primary color rectangles. And that's, I think, his most iconic look that most people are familiar with. It's all over the place. If you don't know his work, you'll start to notice it everywhere once you've seen it, because this primary color kind of abstract approach is was one of the first big approaches to abstract art. So that's my brief art history lesson, for which I'm not really qualified. But I think the role of a mathematical model is similar to this. Like ideally, you start from something that's a real world phenomenon. You try to abstract away what is important about it, and what is evocative, what is interesting, as he's doing with the tree here. He has another parallel series where he's doing pictures of the ocean, abstracting from that also. And so you take the object you're trying to abstract from, and you try to capture the essence of it, or what's interesting about it. And this was what was interesting to him, I guess, was the kind of cubist approach. And he varied on it, and he found different things that were important. He looked at color, he looked at the lines, all these things. In the mathematical sense, I see it as analogous to examining various approaches to studying whatever phenomenon you're interested in, and various simple approaches. And maybe you, in the end, abstract away from even the original problem. You get something new that's of interest for a different reason, or for a decorative reason in this case, perhaps, or for whatever it evokes. Maybe it's, in the analogy, abstracted to the point of being pure math and not applied to anything. The point is, it carries significance and value even when it's simplified. And it's complementary to the very detailed pictures you might also want, but get by other methods. Yes, Eugene.
Can text you. So is the abstraction sufficient condition for model, or is it necessary condition? And how do I know this is actually abstraction is enough condition to write model? Usefulness, how can I?
Yes,
Yeah.
so usefulness is not necessarily in this analogy encapsulated here, right? Maybe if you want to represent a tree, this is like maybe as far as you can go for it to usefully convey that it's a tree, perhaps. But I would say abstraction is a necessary condition for a tractable model. I think, especially for social phenomena, it's hard to have a model that is not abstract, that tries to be very complete without, while still being solvable. I think. Yes.
That's the place where the physicists and the mathematician differ. I have a different opinion here, like when to stop to abstractize my problem. Like, is it like right model? I mean, if this is far away from the social system, then the model is not reflection, actually it was reflection of a social system. Is more like model itself.
Yes, that's a very good point. And that's the art, I guess, is judging when it's enough, but not too much abstraction. And to me, part of the consideration is really, yeah, is it useful, or does it give you insight that you wouldn't get from a more detailed model where you have to use computational methods, for example. But to address that a little bit, here's another example where I think we can think about this interplay between abstraction and accuracy. So you can think about a pendulum bob. Does the mass of the pendulum bob matter? Just a pendulum, example of a pendulum. But let's say we didn't know the physics and we wanted to know like what variables influence its period of oscillation. We'd pretty quickly discover with just playing around with it that the length of the string matters a lot. But we'd probably also see some effects if we were taking data of the mass of the bob, and maybe also like the material the string's made, and who knows what other variables, depends how accurately we're measuring things. So the mass of the pendulum bob in a simple, intro physics level doesn't play any role in the frequency of the pendulum. And that's a key insight. Yet if you started with the complete model, you might miss that insight. If you start with realistic data, even with a small pendulum, you might miss that. The shape of the pendulum bob would also matter. But if your goal is, for example, to develop a really accurate timekeeping device, knowing that that is the theoretical optimum, in the theoretical idealized case that you can create, that you should be able to create a device where the mass doesn't matter, that could feed into your design and your goals in constructing the physical device and engineering it. So I think the role for the math is getting at the key variables in the problem. I think that's the huge dominant role for these tractable models. Unanticipated implications of the conceptual models, that's something that has popped up several times in my work. So language coexistence, this thing I mentioned before, the fact that, at least in that simple model I mentioned, and I'll come back to, that languages do not coexist, that they're driven to extinction, one of them is driven to extinction, was not obvious, despite the fact that sociolinguists had written about the factors that go into that model many times for many years. But when we turn it into something that is concrete and mathematical, sometimes we discover new implications. I think it helps us reason through the implications of the concepts. And it also helps us figure out, well, then what's happening in Canada? In Quebec, there's French, in the rest of Canada, there's English. Why doesn't French disappear? What about Switzerland? So there are these counterexamples, and that also is having a model that says that can't happen shines a light on what's different there, right? Why is this model failing? Highlights what you need to capture. So another example, this one was, to me, actually quite a shock. This handicap hypothesis for deer antlers, peacock feathers, animal ornaments, it implies that the distribution of ornament sizes should be bimodal, that there should be one, they call these morphs in the biology literature, kind of a subspecies, one morph, say of peacocks that have very subdued tails that are not so flashy, and another morph that is very elaborate. And that this should be true for almost every true ornament in the animal world. It's not at all obvious from the statement of the handicap hypothesis, but when you turn this into a concrete mathematical model, it comes out that with almost no additional assumptions beyond what is stated there. So you learn new things sometimes by taking a quantitative mathematical approach. And I say this was a shock to me because we really we predicted this, and I thought, no way this could be right. But then we looked at data, and data bears it out. In every species we were able to find data for. But what else? There are other benefits of mathematical modeling, the tractable modeling. You can improve computation. If you know there's a bifurcation in the simple model, even if you're doing a more complicated computational model, you can expect to see that there also and modify methods for that. If there's critical slowing down in part of the parameter space, you can adapt your methods to these things. So you can improve the computational methods, but you can also understand the results of simulations. In some limit of the more complicated model, it should behave like the simple model, so it gives you a starting point for exploring what more complete models might do, even when you can't analyze them directly. And it also gives you the opportunity to distinguish competing conceptual models. So if I have one conceptual model that says, for example, the distribution of animal ornament size should be unimodal, should look Gaussian, let's say, and another model that says it should be bimodal, based on different fundamental ideas, like different interpretations of this hypothesis or different hypotheses in the first place, I can use a simple model to distinguish that, right? Like the simple model makes these predictions, unimodal, bimodal, and can be enough to distinguish conceptual models. Whoops, I keep hitting the wrong computer keyboard. Okay, so finally into actually not quite yet, the actual math. Modeling social systems. So what is a social system? A little bit more to get to the math. So dynamics tied to the population, dynamics for the individual tied to the population. That's what I consider a social system in somewhat of a mathematical sense. So by that definition, you could say ferromagnetism is a social system because the individual dynamics of one dipole in the material are related to the state and the dynamics of all the other dipoles nearby. So tied to the whole population, or maybe a subset of the population. But in this talk, I'm going to interpret it more of like the standard way. But most of my work, even that's not in what people would typically call social systems, has this characteristic. I think it's one that makes models in general and makes phenomena quite interesting when we have this. This leads to nonlinearity and often unexpected behavior. So sometimes also called sociophysics. That term's maybe less popular these days. Came from French physicist Serge Galam. He phrased the question as, do humans behave like atoms? So, the understanding of the hydrogen atom was a big accomplishment of 20th century physics. And even though there's randomness in the quantum universe, we can still understand mathematically how it behaves. And the big question is, like, to what extent we don't think humans are predictable. I don't think humans are predictable like hydrogen atoms, but some aspects of human behavior are going to be more predictable, some less. So when and to what extent are people predictable? Things like how pedestrians walk when they're not consciously trying to do something, I think are very predictable. Things like opinion dynamics are intermediate. Some of it's predictable, some of it's not. Probably, and there are tons of things that are very hard to predict about people, but that's I see as the big role of understanding social systems with a mathematical approach is figuring out where that's helpful. You could say there's a lot of overlap with behavioral economics. I think there's a difference in philosophy a lot of the time. They're typically starting with data, starting with correlation, and going sort of top down from what the data say instead of bottom up from what are some conceptual models to start from. And these are some popular topics within this category. I've worked on several of them, but and opinion dynamics, left that off of here. But how people's opinions change, how people reach consensus, also a huge one. And I would say the holy grail is quantitative prediction. People want to predict, for example, election results, and people are getting better at that. But I see that as a role for maybe computational modeling. First, we've got to discover the fundamental principles, and I think that is the role of the tractable modeling. Okay, so finally, some successes and failures, as I mentioned in the title of this talk. So I'm going to kind of zoom through these. This is just going to be like a compendium of things. I'll make a couple of comments on them. My point mostly is just like that there's a lot of failures or stuff that hasn't succeeded yet. And then I'll give you the story, a quick story of one of these models that I've mentioned a couple of times. So language death I've already mentioned, though failure in Canada I think feeds into understanding that system. Understanding religious affiliation. So similar, almost the same model works for understanding social group competition in a lot of contexts. So religious affiliation, what I'm referring to there is affiliation with a religious group, not belief in the principles or the religious principles or belief in God, which is surprisingly uncorrelated, strongly uncorrelated with actually belonging to a religious group. So it's really a social phenomenon. The adoption of smoking around the world, and now the dropping of smoking rates in most places. Contagion of obesity. Obesity is contagious mostly through social behaviors that become dominant in different regions. Diffusion of populations in space. So I worked on a project about the diffusion of people through marriage, movement in the Korean Peninsula over the last 1,000 years, mostly through marriage records. But I think there's a lot more to be done there on the history of human migrations.
You are saying it's like the behavior, like the diet that you follow as opposed.
Yes. Well, there is a theory also that some obesity is related to some kind of viral infection. So it could be literal contagion, though I think the evidence is mostly in favor of social contagion. So, but yeah, in the way I'm approaching it, which is social, it's probably better to call it behavior. So I've mentioned some of these evolutionary problems. left-handedness and animal ornaments, gamete sizes, how like, why are eggs, human egg cells about 1 million times bigger in volume than sperm cells? There's a huge, this connects, and it does connect mathematically, though not exactly the same way to the ornament problem, where I'm telling you there's a mathematical inevitability somewhat of a bimodal distribution. In this case, it's bimodality, but by sex. City scaling laws, how crime is crime really big? Worse in bigger cities, and for some crimes that is true. We can kind of get insight into how that can be generated with a simple model. Human pain dynamics. I've been working on sickle cell disease for several years, and people who have this disease, which is inherited, typically have more than half of them have chronic pain, and the pain comes and goes in somewhat unpredictable dynamics. We're trying to develop models for the dynamics of the pain, but it may be generalizable to larger populations of people who suffer chronic pain or even acute pain. I think there's a lot to be done there. There's almost always more to be done on these problems, but political party dynamics, how should the Democrats and Democratic and Republican parties in the US position themselves on the political spectrum to capture the most votes? You can make simple models of this, and it does a surprisingly good job explaining the historical movements of these parties. But in a sense, this is not a success because I wanted to have a continuum. I wanted to explain why there are two parties, and we couldn't quite get that. So there's still a lot more to be done there. I wanted to look at this as a continuum limit of how parties emerge from opinions. And then there's separately the population's political opinions and how those evolve over time. I recently was working on this with my former student, David Sabin Miller, but there's not actually, despite the wealth of data about people's political opinions these days, it's still type of data you need to really constrain models is not quite there yet. So some experiments are needed. And then team formation at conferences. Next week, actually, my student Emma Jidel will be talking about this, the APS March meeting. But there's a lot of similar related questions that are of really great interest to me right now because I want team formation to happen here at NICO. So, so how can we get more interesting teams to form? So here's the long list of things that I've touched on, but not checking the time, but not been successful with yet. Diffusion of innovation. I've had a project around the adoption of internet access around the world. Like, how did the internet spread from one country to another for years? And there are models out there, but I think there's more to be done with a simple tractable approach. Heterospory is very similar to like the plant world equivalent, I would say, of the dichotomy between eggs and sperm. Actually, the same models don't quite work for the distribution of spore sizes. So it's, I think there's lots of interesting math, I think, in the plant world also. It's a little bit, for me anyway, difficult to get into because of like jargon and different philosophies, I think, especially to modeling. But I think there's a lot of opportunity there. More complex language competition. So I talked about this language death, but of course, as I said, there's Canada, there's Switzerland, and then there are countries, a few, not that many, where they're multilingual, where there's multilingual competition happening in a small spatial region, like India, and so I think there's something to be said there that could have implications for language preservation. Interestingly, pedestrians, by the way, these are all ideas that like I said, I haven't succeeded with. So you guys feel free to steal them, please. I'm like happy to have people work on these things. I don't see it as negative. Pedestrians walk faster in bigger cities, according to a paper published in the 60s, I think. And there's a power law, looks like a power law. Is there any potential explanation for this? I think that would be very cool. Trying to catch a train, yeah. But what about multiple big cities that all have trains? I mean, I think that's the core of an idea, yeah. Social momentum, can you quantify this idea in different contexts? I've tried to, it's been used, the phrase is used quite a bit actually. historically and still today, but can you make it a quantitative idea? Geospatial flu adaptation, I was working on this just before COVID, and kind of COVID has overwhelmed all other disease modeling, but this is more of an evolutionary problem. Gender dynamics in science. So this has been somewhat of a success by my former student, Sarah Clifton, actually, who along with some other students from the applied math department, who made a model that tries to disentangle bias effects and homophily in people in advancing through the ranks of science, but all divided into different fields, but also in some of industry. And they're particularly focused on women versus men because that's where the most abundant data is. But I think it's a really important issue to understand what are the core phenomena and which of those two effects is more important. Are there some fields where people really are showing bias, or is it mostly homophily that is preventing minorities from advancing in some fields? Dynamics of happiness has some really interesting data tracking people's happiness over the course of their lives. Can we understand, is there a model for how that's changes over time, which is, it does seem to follow some typical patterns. Subjective time, this is a really fun one, there's also a pretty universal experience that the years pass more quickly as you get older, but it's very nonlinear. People have tried to measure this. There have been a few semi-experiments on like how long a minute feels for people of different ages, and there's consistency across people, pretty good consistency, but it's not clear. It's not like logarithmic scaling, as many things with human experience are. So it's not clear. And why would that be? Evolution of the HPV virus. This is something complicated to go into here, but metabolic rate scaling for pediatrics is really important. And I was working on this with both these were projects with clinical research doctors, actually, clinical practitioners. Particularly on this one, it's really very important to give pediatric patients, kids who have surgery, the right amount of nutrition after the surgery when they're recovering. You give them, interestingly, if you give them too much, it's worse than giving them too little. But you have to have some idea of how much they need and current models are terrible. That's the state of the art is terrible, and it can almost certainly be improved on. Popular music shows oscillations in all kinds of interesting things. For example, gender dynamics, like female vocalists become dominant for periods of time, and then male, and all kinds of other, everything you can measure about music shows these interesting oscillations. It connects to other, I would say, fashion problems. But I think there's also two really fun and interesting problems that are open about, one I will call the two gender problem. So why do we have two human genders? I should have changed that to sex. I thought I did, actually. Human sexes. Biological sex is, for the most part, male or female. And yet, if you look at some species, there's like 11 sexes, 81 in some kinds of funguses. Why do we, and the way that works is typically like you can mate with, watch the clock, you can mate with almost all the others except for your own sex, and they're just numbered. So this connects, I think, to the gamete size problem that I've worked on in the past, but it's not a direct generalization. I don't think it's understood. There are some theories. And the bigger, huge problem, why is sexual reproduction so much more efficient than asexual? Asexual reproduction exists in nature, but it's very uncommon. So why, at least in larger multicellular organs. So why is it so much more advantageous? There are a lot of theories that have existed for quite a while on this, but I don't think they've been made quantitative, and I think there may be new insight to be gained there. Psychological pricing. Why are why do we want to buy things when they're $2.99 rather than $3 or $2.95? This again is well known and obviously implemented all over the place in the marketplace, but understanding the quantitative impacts of pricing is, I think, missing. And then this last one Emma talked about a couple of weeks ago, understanding fashion. We have this really interesting data set on the history of women's fashion in some quantitative ways, but it touches on the bigger picture of creativity and how people generate new ideas over time. So in progress, I think it's not that it is not that is failed or anything, but there's a lot to be done. So, okay, I'm gonna have to zoom through this, but anyway, some thoughts. So I forgot to point out the list of unsuccessful things that I've at least worked on, at least for some amount of time briefly, is longer than successful things. And I'm sure I left out a lot of stuff that I couldn't remember at this point. So, so I think part of science is making mistakes. I think you learn stuff from the mistakes also. Okay, let me give a little bit of a super fast, which is never a good thing to say in a talk, but a super fast run through of like what I mean in detail of one of these examples, like a competitive social system, which is something I've used for modeling many things in the past, languages, religions. I think this type of approach could be used for all kinds of other systems. The evolution of left-handers also takes a very similar approach. Let me use this language example. So today there are on the order of 6,000 languages spoken in the world, but most of them are tiny and disappearing. There's no clear method for triage. Here's some data sets on the problem in like, in the larger of these languages. The smaller ones, there's just no data. So how can you take, there are two big phenomena, I've mentioned this before, that sociolinguists have identified in the past that we'll try to encapsulate in a model. One is that people switch to languages with more speakers. The other is that people switch to languages with higher status. So, and status can include advantages due to educational opportunities, economic opportunities, security. Maybe you're not allowed, you get thrown in jail if you speak the wrong language. That's happened historically many times. So, so this function is the rate of transition from language Y to language X. And this is a way of deriving a simple differential equation model. So I know how do the number of speakers of X change in a short amount of time. Start with a current number X and current number Y, and for each of the two languages, and then we have this rate of transition between the two. We're assuming based on the conceptual model that it depends, these transition rates depend only on the fraction, lowercase x, that speak language X, and the status of the language S. So you can convert things to fractions by dividing through by the total number of people in the population, and we can get rid of this Y variable then, which is the fraction Y speakers, by replacing with 1 minus X, so the total population is 100%. And so there's this equation I had up earlier. And the key here is now to just impose a few more assumptions that transition rate from Y to X is a function of these two variables, the variable and the parameter, I would say S, variable X. And that there's this symmetry, which says that no language is better intrinsically at communicating than any other. I think that's a very mild assumption, widely accepted. Every language can invent words if it needs to. And then there's these two assumptions. This is really from the sociolinguists that if more people speak your language, that, well, you're probably of switching to that. Sorry, if more people speak language X, you're probably switching to that from language Y is going to rise, at least marginally. It's not going to shrink because you have more opportunity for communicating with people. And similarly with S, if it's got a higher status, that's going to increase the transition rate to that language. And then no one switches to language with no speakers, no one switches to language with no status. These are idealizations. There are, in fact, historical times when people have tried to invent languages or switch to dead languages. But for a simple model, we make these assumptions. That's it. Those are the assumptions you need. And then you can show that for any smooth transition function, Pyx, there's 3 equilibria and only 2 are stable. Everyone's speaking language X, everyone's speaking language Y, or this balanced one in the middle is unstable, where there is a coexistent state. So I'm going to skip these cartoons of what's happening. This is the picture I had up before. Unfortunately, I'll have to skip some of the music here, but let me just go over the the limitations here, right? There's a million simplifications that you could call oversimplifications, right? No bilingualism allowed. There's only one mother tongue in this model. Only 2 languages, no spatial variation, no social networks, but still it works pretty well. I didn't really show the data. It works pretty well in comparing to data. So, I am actually surprised by how well it works. And one question in follow-up work that I did on this model is, why does it work this way? What if you include social networks? What if you include spatial information? And it turns out that those generalizations actually still maintain this property for the most part. It's very difficult to stabilize a bilingual society. The thing that can work in almost any of these models is active control. So if you can promote a minority language, I think that's what's happening in Canada. That since the 1970s, in Quebec, they've strongly promoted the use of French through advertising on TV, through laws that say children of one French speaker must go to a French-speaking school. Advertising can be in French. It cannot be exclusively English. It can be in French or bilingual. So with active control, I think you can preserve these things, and that's something you get out of these types of mathematical models. And there are some efforts to do this. For a bunch of the data that I skipped over here was from the Quechua language in Peru. These are, maybe I do have some time to play a little bit of the music. There's traditional music in Quechua. Quechua is one of the fastest decreasing languages in the world, despite being a very sizable minority language. It was the majority in many parts of Peru until recently, and Bolivia, and Ecuador, several other countries. It was the language of the Incan Empire and was associated with farmers, basically. So it was very low status. People in cities didn't want to speak it because they think of it as farming language. But yeah, attempts at revitalizing it. So here's the audio portion of this. And this is, oops, even that music is mixture of Spanish and Quechua. But then, yeah, there have been some. This is sometimes a shock to people who speak Quechua because they just assume nothing modern can be in it. And oops, and then the third one was this. These types of things are ways of raising the status, and it's an attempt to try to protect the language and keep it from disappearing, though will it be enough? So so that's kind of the summary of the talk. It's a big ad for tractable mathematical modeling. And even if you don't want to do that, try to partner with people who do it. I feel like it's got a big, and if you're doing it, try to find partners who have other approaches. I feel like it's got huge potential and is underutilized, especially in some areas of interdisciplinary complex systems research. So, so my last bit is just the pitch for NICO as a place for intersections on this Venn diagram. I think this is at Cambridge or Oxford, I forget. There's these windows dedicated to former faculty, and Ben's got the Venn diagram on his windows. A place for intersection on this Venn diagram of many different approaches to modeling and understanding the world. I want to catalyze new collaboration, so I want to get people together. If you're looking, for example, for a place to just go and hang out once a week or something, or once in a while, to be in a different place from where you usually sit and do work, I want NICO to perhaps be that place. We're thinking about making some new space for collaboration. But even more, I want to hear your thoughts if that would be useful for you. If there's other things that you would like NICO to be doing to promote complex systems in general, social systems even. So please send me an email. Give me your thoughts. You can meet in person, wherever you want, or just do it virtually, do it by email. But I want to hear from people. So thank you guys all for hearing my thoughts here.
It's a great talk. Do you have any questions? Questions?
So, I think sometimes it's probably easier to know whether if your model is correct or right. How do you know if your model is wrong? Because when you have the data and then you are fitting a model, and then you have some metric, right, to know this is accurate because it fits the data. How do you know it's wrong?
Yeah, good. I think that's a very good question. How do you know when the model is wrong? So I think there's two approaches you can take that. One is you can, I would say kind of the physics approach is you have data, you plot the data and the model on the same axis, and you say, yeah, they kind of look similar. And if they're similar enough, it's not wrong, not too wrong. There's a more quantitative approach you can take to that. You can try comparing your model to null models and using some kind of like an Bayesian or ICAE information criterion that analyzes models for complexity, for having a lot of parameters, and lets you select the best of several competing models, including some simple model, which would say like, this conceptual model is not right, it's just random. That should be a null model that you want to compare to. So there's more than just information criteria. You can also do cross validation. It's more of a statistical approach to that. But I think that is a key step, having data. Without data, modeling things like social systems is tough. There's an old saying I've heard from, that comes from physics, which is, let me see if I can get it right. Nobody believes in a theory except for the person who came up with it. Everybody believes in an experiment except the person who did it. So those who've done experiments, I think, will find that funnier. But I think both parts are somewhat true. That that the theoretical parts or the modeling, mathematical modeling parts, often require data to convince people that it pertains to reality.
Can I be a little bit more extreme about the?
Sure.
Yeah. So I always consider all models are wrong. Some models are less wrong. Some models are less right. But all models model cannot be a reality. It shouldn't be representation of the reflection of. I mean, it's a reflection of reality, but it's actually some dimension reduction and some abstract version of reality. Now, the abstract version can many different forms, many different representation. It could be a representation of the interactions of reality, or representation of the herding behavior of like a choice of the order parameter. So all models are wrong. It's just like some models are more less wrong, and some. But most important point for me is some models are more useful than the others.
Yes, I think that's a great point. Yeah, I don't know who said, was that NICO Fermi? A lot of things have been attributed to him, right? All models are wrong, some models are useful. But yeah, I think you make an excellent point. So it's always going to be wrong to some extent. So the question is what's the trade-off between accuracy and parsimony, I think. There's another, I think it was von Neumann had this quote. Oh, we're tossing out quotes. I should wrap up. But he said, give me 4 parameters and I can model an elephant. Give me 5 parameters, I can make him wave his trunk. So so there's this problem the problem he's pointing out is overfitting. And so there are rigorous ways of trying to counteract that, right? And to balance the parsimony against the accuracy, but it's not always that it has to be done that way. I think the approach of saying this is good enough and it's a beautiful model is a very valid one.
It seems to me like what you described was a lot of underfitting almost. Like you try to tune your model so that it's not overfit, it's not underfit. And as you mentioned, there's a lot of ways to do that. But it seemed like this talk almost, you were favoring that you should underfit your models and capture some general trend, or that this is what mathematics tries to do, and then applies it to a broader context and see where that fails. And that might show you what's interesting. Is that a fair representation of what you described?
That's interesting. I haven't thought about it as underfitting explicitly, but I would say that's not unfair. I think of it maybe more as underparameterizing, trying to, in a way, there's a statistical technique called lasso. The goal is to like eliminate extraneous parameters that aren't really necessary, right, to avoid overfitting. And I would say it's more of a with analytical modeling like this, it's more of an art than a science, like where lasso has standard techniques. But yeah, trying to see what's the minimum you can get away with and still learn something. So I could call that underfitting.
With that, I would love to, but we actually are over the time, so you can actually come back, have a discussion. Thank you very much, and thank you very much. Let's give me a good round.
Thank you all for coming.